In this video, we'll be talking about the telescoping series. The telescoping series is actually a series that is quite simple and unique in the way that it works. So most telescoping series will be written in some form like this. And the thing that you want to note here is that there's actually two pieces to this series. There's the 1 over 3 to the k, and then there's minus a 1 over 3 to the k plus 1. So what you really do with a telescoping series is you're not recognizing that it's a telescoping series until you start writing out the values. Really what you're doing with a telescoping series is you're really using the limit of partial sums. So for me to do the limit of partial sums, I'm going to actually have to write out all the terms. So if I plug in 1, I'm going to get 1 over 3 minus 1 over 3 squared. And that's the way that I'm going to write almost all of these terms. I write out the second term. When I plug in 2, I'm going to have 1 over 3 squared minus 1 over 3 to the power of 3. Now the thing that you'll hopefully notice quite quickly is that this is negative 1 over 3 squared plus 1 over 3 squared. So these two terms will actually cancel each other out. Then I'm going to have plus, it'll be 1 over 3 cubed minus 1 over 3 to the 4th. And this will continue on again forever. So it'll be plus dot 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 plus, eventually I'll get to 1 over 3 to the power of n minus 1 over 3 to the power of n plus 1. Over here you'll have a 1 over 3 to the n. Over here you'll have a 1 over 3 to the n plus 1. Those will be alternating signs, such that it plus dot 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 continues on forever. Now, if we were to try to evaluate s sub n, again, trying to find the limit of partial sums, we would conclude that as I continue all of these values, this is the first term, the second term, the third term, this would be your nth term, s sub n, this is going to cancel out with this is going to cancel out with this, and all the middle terms are all going to cancel out. And I'm going to be left with the s sub n is 1/3, technically minus, this is going to cancel out with the previous term, minus 1 over 3 to the power of n plus 1. But if I'm going to try to take the limit as n goes to infinity of this, the limit as n goes to infinity of 1 over 3 minus 1 over 3 to the n plus 1, well, that's going to be 1/3, that's not going to change, minus, this thing is going to go to, well, 0, because it's 1 over something getting very, very large. So this is going to be 1 over 3 minus 0, which is really just 1/3. Now, it's important to notice that this happened to be the only term that remained. It is not always the case that the first term is always the term to remain. There might be other terms in here that are going to bounce around before you conclude that all of the terms will end up canceling out. But in this case, if I can identify or conclude that this is a telescoping series, and these terms here will start canceling out entirely once it gets to a certain point. Again, in this case, it happened to be the first term. The second term, they all started canceling out. Then it is a telescoping series, therefore will converge. And in this case, it will converge to this limit of partial sums value, 1/3. So another example we could do is it would be k equals 1 to infinity of, say, 1 over k plus 1. Now you're looking at this and saying, well, wait a second, that doesn't look like the same situation we had before. If I start plugging in values, I'm going to have 1 over 2. The next term is going to be 1 over, if I plug in 2, I'm going to get 2 and 3, so 1 over 6. And if you continue that pattern, you'll notice that, again, it's not actually going to show any terms canceling out. But what you might recall from Calculus 1, from pre-calculus a little bit, and from your work on partial fraction decomposition with integrals in this class, that this fraction can be torn back apart. So I'm going to go ahead and say that this is equal to, using partial fraction decomposition, again, we use that specific method in Calculus 2 when we're trying to evaluate specific integrals. Now we're going to use it again. And it tears apart into, and again, I'm not going to go ahead and do all the work in there, but eventually when we're done, it'll tear apart into this. If you do the partial fraction decomposition where this is a and this is b, and you do the math and you solve for a and b, you get 1 and 1, or 1 and negative 1. So if this is the case, I'm going to go ahead and, well, write out the terms again. This series is technically then equal to 1 minus 1/2 plus 1/2 minus 1/3 plus, and so on and so forth. Now again, I would generally recommend writing out probably 3 or 4 terms until you feel comfortable that it's definitive that this cancels out with this cancels out with this, and all the other terms afterwards technically cancel out until you get down to the nth term, which is 1 over n minus 1 over n plus 1. This is again a minus sign. This 1 over n will cancel out with the previous term. This will be left, and we're going to, again, use the limit of s sub n, the limit of partial sums. The limit of partial sums is the limit of what's left. 1 minus this goes to 0. Therefore, this is a telescoping series, and we can identify clearly it will converge, in this case, to 1. So this is by telescoping series, or I will accept by partial, the limit of partial sums is equal to 1. There are other versions of telescoping series, but in most cases, this is what you're going to have to deal with. You're going to have to, if you see something that looks like it could be, again, a partial fraction decomp and torn apart into its two separate fractions, but if anytime I see a summation such that it has two separate fractions, I'm going to assume that it might be a partial fraction decomp, and I'm going to start working my way through it. There is another way to do this problem. You'll notice that this problem right here is technically the subtraction of two geometric series. And there is a way for us to work with two different series in one case and how that series might converge using the rules of multiple different setups. For instance, again, I could use that this is a geometric series and will converge. I can then use this as a geometric series and will converge. And then since this will converge to something and this will converge to something, I can subtract the two values from each other, concluding that I will end up with, once again, converging to 1/3.